Good morning, everyone. In today's lecture, we are going to discuss about the electronic configuration of all the blocks of the element, whether the elements are S block, P block, D block, or the F block elements, followed by the different type of the shells which get involved during writing of the electronic configuration, about the different type of valence shell electrons, whether they are the lone pair, bond pair, and the different factor which affects the trend in the size and the other properties, means screening effect and the penetration power. So let's discuss all these factors one by one. First of all, we will discuss about the electronic configuration. So means what do you mean by the term electronic configuration? Means we want to configure the electrons in different shells or the subshells or the orbitals. So what type of arrangement should be given to these electrons in different shells, subshell, or the orbitals? Which type of rules will be used will be discussed in the chapter, that is the atomic structure. But here the definition of the electronic arrangement is the arrangement of the electrons in different shells, subshells, and the orbitals by using the Above principle, the Pauli exclusion principle, and the Hund's rule is called as electronic configuration. You can see here the electronic configuration of the different groups present in the periodic table. First of all, we will see about the group number 1. In the group number 1, the elements are hydrogen, lithium, sodium, potassium, rubidium, cesium, and the francium. Now we will write the electronic configuration of these. The electronic configuration of the hydrogen is 1s1, like that we will write them. But before that, we will see the different elements of the group 2. The different elements of group 2 are beryllium, magnesium, calcium, strontium, barium, and radium. We have already told you about how can you learn these elements of group number 1. Halina K. Rabi Shashi friend, that's the basic trick for the group number 1. HLINA Halina, K RB Rabi, CS Shashi, FR friend. Similarly, there is a basic trick behind the group number 2 learning. That is the beta Mange, BE beta, MG Mange, CA car, SR scooter, BA Bap, RA Roy. Beta Mange car scooter, Bap Roy. Like that you can learn all these group number 1 and group number 2 elements. So what is the configuration of hydrogen? The configuration of the hydrogen is 1s1, means there is one electron that is present in first shell, and the subshell is s, and the number of electron is 1 because the atomic number is 1. What is the meaning of that first one here? First one here that is present on the left hand side in the 1s1, that one means first shell. And what do you mean by that next S? Means in the first shell, there is S subshell on which the electron is present. You will write these electron in raised to the power. So 1s1, that's the configuration of the hydrogen. Next, lithium. We are just writing here the valence configuration. Because the complete configuration of the lithium is 1s2, 2s1, we are just writing the valence configuration. Just increase one number means the number of shells goes on increasing on moving down the group. So the valence configuration of the lithium is 2s1. Similarly, the valence configuration for the sodium is 3s1. 3s1 means you can see in the above diagram, in the center there is a nucleus. After that, the first shell where two electrons are present, you can see in case of the lithium configuration 1s2, 2s1. So the next one is second shell. In second shell, S subshell, one electron is present. We have just shown you about the lithium 1s2, 2s1. That's the complete diagram for the lithium having the atomic number 3. For valence configuration of sodium is 3s1. The valence configuration for potassium is 4s1. The valence configuration for rubidium is 5s1. For the cesium is 6s1. For francium is 7s1. Right? Now we can write the electron configuration for the beryllium. For writing the configuration of the beryllium, the complete configuration is 1s2, 2s2. Means just fill one more electron in that position here. As you can see, the above diagram is for the lithium. If you fill one more electron in the second shell, in the S subshell of the second shell, means one more electron with half spin in the opposite direction, then that will be the 2s2. right? So the next valence conjugation is for the magnesium. So what is the valence conjugation for the magnesium? 2s2 for the beryllium, magnesium for 3s2. For calcium, 4s2. For strontium, 5s2. For barium, 6s2. For radium, 7s2. So in this way, you can learn the valence conjugation for group 1 and the group 2 elements. So the general configuration of S block element is NS1 to 2 because 1 for the group 1 and 2 for the group 2. So S block has two group 1 and the group 2. We have already discussed about the general characteristics of all the blocks, S block, P block, D block and the F block elements. Next, we will see the electron configuration of the group number 13, 14, and so on. So for the group number 13, the elements are boron, aluminium, gallium, indium, thallium. For the group number 14 are carbon, silicon, germanium, tin, and the lead. The configuration for the beryllium is, for the boron is, sorry, B for boron, atomic number 5, 1s2. In place of 1s2, we have just right here the helium because 1s2 is the configuration of the helium. So the configuration is 1s2, 2s2, 2p1. The valence configuration is 2s2, 2p1. Now we will write the valence configuration for the other element also. You can see the diagram for the boron here. 1s2, you can see here the 2 electron present in the first shell and the 2 electron present in the second shell of S subshell of the second shell, 2s2. And 1 electron is present in the P subshell of the second shell, that is 2p1. You can see the diagram. Now the configuration for the aluminum, 1s2, 2s2, 2p6 means the 10 electrons, 10 is the atomic number of the neon. So 10, we have just written here the neon. After that 3s2, 3p1 means that's the valence configuration, valence. Just increase the number of the shell, just increase the number of the valence shell, the configuration will be of next element in the same group. What's the valence configuration for the gallium in the same way? 3s2, 3p1 for the aluminum. So the 4s2, 4p1, 4s2, 4p1 for the gallium. We have written here the 3d10 because in case of the aluminum, the configuration is 3s2, 3p1 and 3d0 is vacant. That 3d becomes the fulfilled in case of the gallium. So we have just written here. Next, the indium. In case of the gallium, you can see here the 4s2, 4p1 is the valence configuration. That's why the next element configuration is 5s2, 5p1 for the indium. Because in case of the gallium, the vacant orbitals are, because the last shell is 4 shell, because that is the fourth period element, gallium is the fourth period element, because the last shell is fourth shell, so it is the fourth period element. And in the fourth shell, you all know the remaining vacant orbitals are 4s, 4p. They have the electrons 4s2, 4p1, but the vacant are 4d and 4f. And that 4d becomes fulfilled in the next element case, that is the indium, atomic number 49. That's why we have written here the 4d10, 5s2, 5p1, right? Because in the gallium there is 4d and 4f. So where the F is present? F is present in the next element, that is the thallium here. So the valence configuration for the thallium is, in, as you can see, the valence configuration of the indium is 5s2, 5p1. So the valence configuration for the thallium is 6s2, 6p1. Why we have written that one? Because in case of the indium, you can see the 5s, 5p, there are the 5d, 5f, 5g. So the next one after that 5p, that the vacant one is 5d, that the fulfilled here. And before that, the remaining one in case of the gallium, there is the 4p, after 4p, 4d and 4f. 4f is also filled here. So the fulfilled F subshell is present in case of the thallium, not in the above one. So that's the basic fact you have to learn. So the two things you have to learn here is the element in group number 13 which has no d orbital, that is the boron, because it is the second paired element. You can see just by writing the electron configuration for the boron 1s2, 2s2, 2p1, because it is the second period element, and in the second period element means it has only two shells, and in the second shell there is only s and p, no d, no f and so on. So What it means? Means boron has no vacant d orbital. Similarly, for the thallium, you can see here in the configuration, it has the fulfilled F subshell, right? So, in the same way, you can write the electron configuration of group number 14 just by increasing one more electron in the valence shell. In case of the boron, the number of electron in the valence shell are 2s2, 2p3. There are the 3 electron. So that's the here, the group number 13, the last numeral value is 3, means 3 valence electron here. In case of group 14, one more electron. So what you will write, what the slight change in the configuration of the next group element, which are present in the same period, means boron is the second period element, carbon is the second period element, aluminum is the second period element, silicon is the second period element, aluminum is the third period element, silicon is also the third period element. So just increase one more electron, and that will be the electron configuration for the carbon. Just see here, we have written here the configuration for the carbon. You can see 2s2 2p in place of 2s2 2p1 for the boron. We have just written here 2s2 2p2 for the carbon, right? For the silicon, what you will write? In place of 3s2 3p1 for the aluminum, you will write here 3s2 3p2. Similarly, for the gallium, configuration is 4s2 4p, valence configuration is 4s2 4p1. For germanium, that will be the 4s2 4p2, right? The valence configuration for the indium is 5s2 5p1. You just write here the 5s2 5p1. In spite of that, you can also learn it like that. The valence configuration for the carbon is 2s2 2p1. On moving down the group, the number of shell will increase. So the configuration for the silicon will be 3s2 3p2, one more shell increase. Germanium, one more shell increase, 4s2 4p1. 14, one more shell increase, 5s2 5p1. And for lead, one more shell will be increased, that is the 6s2 6p1. Right? So that's the electron configuration of group number 13 and the 14. Next, about the group number 15, 16, 17, and the 18. You can also write the configuration in the same manner. The electrons in the group number 15 are nitrogen, phosphorus, arsenic, antimony, and the bismuth. Just increase one more electron in comparison to the group number 14. In carbon, you can see 2s2 2p3. So what here? That is the 2s2 2p3. The next element, first of all, we write here the name of the elements of these different groups. For group number 16, the elements are oxygen, sulfur, selenium, tellurium, polonium. For group number 17 are fluorine, chlorine, bromine, iodine, and the acetine. For group number 18 are helium, neon, argon, krypton, xenon, and the radon. Right? Now we will write the electron configuration for the, first of all, about the group number 15. The first element in group number 15 is the nitrogen. The configuration is 1s2 2s2 2p3, means one more electron in comparison to carbon because they are the second paired element. So the next element configuration, valence configuration will be phosphor. The phosphorus, that is the 2 in place of 2s2 2p3 of the nitrogen. We will just write here one, increase the number of the shell, 3s2 3p3. For arsenic, 4s2 4p3. For antimony, 5s2 5p3. For bismuth, 6s2 6p3. In the same way, we'll write the configuration for the oxygen. For nitrogen, that is the 2s2 2p3, increase one more number. The configuration becomes 2s2 2p4. That's the valence configuration for the oxygen. For sulfur, 3s2 3p3. For selenium, 4s2 4p4. For oxygen, 2s2 2p4. For sulfur, 3s2 3p4. For selenium, 4s2 4p4. For tellurium, 5s2 5p4. For polonium, that is the 6s2 6p4. Right? In the same way, we can write the electron configuration for the fluorine, that is the first element of the group number 17. The configuration becomes 1s2 2s2 2p5, means one more electron enters into the 2p. So the next, for valence configuration for the next element, that is for the chlorine, is 3s2 3p5. For bromine, 4s2 4p5. For iodine, that is the 5s2 5p5. For acetine, the 6s2 6p5. Right? Now we will write the electron configuration for the group number 18. The exceptional case is the helium, whose configuration is 1s2. Now we will write the electron configuration of the next element, that is the second paired element of the group number 18, that is the neon, the 1s2 2s2 2p6. Right? So the valence configuration is 2s2 2p6. Just increase one more shell for the next element, that the argon one, 3s2 3p6. For the krypton, 4s2 4p6. For xenon, 5s2 5p6. For radon, That is a 6s2 6p6. Why we are writing here the valence configuration? Because generally during drawing the structure geometry of the different compound, for example, group number 18, XCF2, XCF4, we just write the electronic configuration, valence electron configuration. So in this way, we can write the electronic configuration of any of the element. For example, in group number 18, first simply write the electron configuration of the neon, that is the 2s2 to p4. 6, just see the position of the xenon, means of neon, after that argon 3s2 3p6, krypton 4s2 4p6, xenon 5s2 5p6. Like that we write it in our mind, and then directly we can write directly the valence configuration of the xenon in the examination, 5s2 5p6, like that. Okay. So that about the electronic configuration of these element, group 1, group 2, S block. Now these are the P block elements, group number 13 to group number 18. So the arrangement of the electrons in different shells, subshell, and the orbitals by using the different rules, that is our Bohr principle, which states that the electrons are always filled up in the increasing order of their energy. Means electrons are first of all filled up in that shell or the subshell or the orbital which have the least energy, because lesser the energy, more will be the stability. Because the shell which is present near to the nucleus, when the electron enters into it, it will cause more interaction, more attraction with the nucleus, means more energy will be released outside. So the system energy will be less. So the lesser the energy, more will be the stability. That's why electrons are filled up in that subshell which is present nearer to the nucleus. Because if the electron is present in that subshell which is present near to the nucleus, will cause more attraction with the nucleus, which results in the release in the energy. More release in the energy means more attraction, more energy released, and thus lesser energy will be of the system and more will be the stability. So that's the reason here behind the Hofbauer principle, right? After that, you will use here the Pauli exclusion principle. You can see here in an orbital there can be a maximum of 2 electrons of opposite spin. So that's why that is the principle that is called as the Aufbau principle. After that, you have used the Hund's rule, which states that among the degenerate orbital, like the p subshell here, you will first of all fill these degenerate orbital subshell singly, then the pairing will start. Among the degenerate orbitals of the p, d, and the f subshell, electrons are first of all filled up singly, then the pairing will start. So the general electron configuration for the p block element here is ns2 np126. ns2 in all these elements, you can see the valence in the valence shell configuration, ns2 in all these elements, ns2. Number n means number of the shell, that goes on changing on moving down the group. Similarly for np1 to 6, 1 for group 13, 2 for group 14, 3 2p3 for group 15, 2p4 group 16, 2p5 group 17, 2p6 for group number 18. So that's why np1 to 6. Okay. Now we have the simple basic facts behind these different group elements. The group 1 element called as the alkali metals, because their hydroxide, when they dissolved in water, they gives the OH negative ion. So they are basic, so they are alkali metals. Group 2 element are called as alkaline earth metal because they are present in the earth crust, and also their oxide, when dissolved in water, produces the hydroxide, which further gives the OH negative ion. So they are alkali, they are basic, and they are present in the earth crust. Their oxide are present in the earth crust. Because of that reason, they are called as the earth metal, alkaline earth metal. All the group 1 and group 2 elements are the solid and they are the metal, right? So group 15 elements called as the Nicogen due to their suffocating nature. Group 16 called as the Chalcogen because they form the ores, oxides, the sulfides. They are present in the earth crust, so they called as the chalcogens due to their ore forming nature. Group 17 called as a halogen due to their salt forming nature because they are most non-metallic. They form the ionic bond with the group 1, group 2 elements. So because of their salt forming nature, they called as the halogens. Group 18 elements are called as the noble metal due to their low reactivity. Initially, they called as the inert gases because initially there is no research whether they can form any compound or not. But after the Neil Bartlett experiment, it has been proved that the group number 18 elements, some of the group 18 elements like the genome, they can form some compounds. So because they can form some compound, but they have the fulfilled stable conjugations. So the word here used is the more proper is the noble gases. They are less reactive, means they have some reactivity. They are less reactive. The second paired elements are nitrogen, oxygen, fluorine, neon. You can see here. The boron is also the second paired element. The carbon is also the second paired element. The second paired element, that is boron, carbon, nitrogen, oxygen, fluorine, neon, they don't have any d subshell, vacant d subshell, absence of d subshell. They have no d subshell. Next, the last element in the group, that is the group number 13, that is the thallium, group number 14, that is the lead, group 15 bismuth, group 16 polonium, group 17 astatine, group 18 radon. All these elements have the unusual property due to the presence of the fulfilled F subshell. Fulfilled F subshell, you can see here in all these elements, there is 4F14. You can see here the 4F14. They have the fulfilled F subshell. So they will show something unusual properties. The last element of group number 16, 17, and the 18 means group 16 polonium, 17 astatine, group 18 radon. They are radioactive also. All element in group number 15 shows the allotropy except nitrogen. Nitrogen shows no allotropy property. Allotropy means the existence of an atom of element in more than one forms. That called the allotropy. Like phosphorus exists in white phosphorus, red phosphorus, black phosphorus, right? So the other element shows the allotropy, but nitrogen shows no allotropy. Group number 16, the oxygen has two allotropic form, that is the ozone and the dioxygen, O2 and the O3. Similarly, sulfur, monoclinic sulfur, triclinic sulfur, like that, these are the allotropic form of the sulfur. Group number 17 and 18 element shows no allotropy property. Next, we will see among the group number 13 to 18, you will see the nitrogen is a gas, oxygen is a gas, fluorine is a gas, nitrogen in group number 15 is a gas, oxygen in group number 16 is a gas, fluorine and chlorine group number 17 are the gases, and all group 18 element are the gases. In group number 17, the only non-metal liquid is the bromine. The other are the solid one. The radioactive elements are polonium, astatine, and the radon. We already told you. The metals are aluminium, gallium, aluminium group 13, gallium in group number boron, aluminium, gallium. You can see here gallium. So means aluminium, gallium in group number, indium, thallium. These are the metals in group number 13. Bismuth in group number 15, that is the metal. Polonium group number 16, that is the metal. Non-metals, these are the carbon, silicon, nitrogen, phosphorus, oxygen, sulfur. Here are some names of the element which are the non-metal here. Metallides are the boron, germanium, arsenic, antimony, selenium, tellurium. These are the metallides whose characteristics are between metal and the non-metal. Next, we will see about the number of the electrons, different type of electrons which are present in the valence shell of the group number 15, 16, 17, and the 18. You can see the valence conjugation of the group number 15. Here is the valence conjugation for group number 15, and the first element of group number 15 is that is the nitrogen, that is a 2s2 2p3, 2s2. You can see here the two electron, that is one orbital, that is 2s. And two electrons are present, that is the 2s2. And 2p3 means that is the 2p subshell having the three electrons following the Hund's rule. One electron in each of the p subshell orbitals, that is the 2p3 here. Okay, so the next one, group number 14, increase just one number. Again, use the Hund's rule. Means among the degenerate orbital of the p subshell here, first of all, electron filled up singly, 1, 1, 1, and then pairing will start. You can see here. So that's the configuration of the oxygen valence conjugation. 2s2 means 2s electron here, and 2p4, 1, 2, 3, and 4. Then pairing will start according to the Hund's rule. That is the 2p4. Similarly, in case of the group number 17, first element is fluorine. So the valence configuration diagram for the fluorine, 2s2, 2s2, and 2p5, 1, 2, 3, 4, 5. Means according to the Hund's rule, right? Group number 18, that's the neon here. valence configuration 2s2 2p6 2s2 and 2p6. But you've seen here among these elements, you can see there are two type of electron in the valential. Some are unpaired electrons and some other are the paired electrons. So these paired electrons and the unpaired electrons, they have special naming. So these unpaired electrons, these are used in the formation of the covalent bond. So these are called as the bond pair electron, BP electrons, we generally see here, and that called as the valency of the element. The covalent bond formed by an atom of element called as their valency. Valency didn't mean only due to these, generally due to these formation of these bond, that the covalent bond here, but sometimes the element may form the coordinate bond with the help of these lone pair, means electron which present in the paired form in the valential. So what are the lone pair electrons? These paired electron present in the valential called as a lone pair electron. These pair electron also present in the inner shell also, because all get paired, but generally that term is used for valence shell. So in the valence shell, two type of electrons are present, that the unpaired electron called as the bond pair electrons and the paired electron that called as a lone pair. Right? So in group number 15, you can see there are the three bond pair and the one lone pair. In group number 16, you can see there are the two bond pair, two lone pair. In group number 17, you can see here, there are the one bond pair and the three lone pair. In group number 18, you can see there are the zero bond pair. You can write here the zero bond pair and the four lone pair. You have to write here four, just change their position. Okay. Next one, the valential electron. What are these valential electrons? The electrons which are present in the outermost shell are called as the valential electrons. These all are the valential electrons because they are present in their outermost shell. And these valential electrons are of two types. There are the bond pair electrons. The unpaired electrons which are present in the valence shell, which take part in the formation of the covalent bond, they called as the bond pair electrons, right? The lone pair electrons, the paired electron, these all paired electron, you can see here in the diagram. These all paired electrons which are present in the valence shell and they do not take part in the formation of a covalent bond. We are saying here the covalent bond, which do not take part in the formation of covalent bond, are called as a lone pair electron. While these lone pair electrons sometimes can be used in the formation of the coordinate bond, or you can say the dative bond, right? So, but sometimes also when these in the next element, because these here is the configuration for the second paired element, like the group number 15, we have shown diagram here for the group first element, that nitrogen, oxygen, fluorine, and the neon here. For the next element, that of third paired element, that is for the phosphorus, if in group number 15, that's the configuration, that's the valence configuration also for the phosphorus, 3s2 3p3 3s2 3p3. But in the phosphorus there is the 3p3. After 3p3 there is vacant 3d orbital. Means if we draw here the vacant 3d or orbital, after that, that is that one 3p1. So what will happen means that lone pair electron can be unpaired due to the presence of that vacant d orbital. So in the next element, that these paired electron may be unpaired. So the covalency will increase, means tendency to formation of the covalent bond will also increase, because the number of unpaired electrons after jumping of these paired electrons into the vacant d orbital, which is present after that 3p here, if you draw here. So then the number of unpaired electron will be 5. That's the group number 15. The last letter is 5. 5 means the maximum number of electron present in the group number 15 are 5, and these maximum unpaired electron may be present in the phosphorus after jumping that S electrons into the vacant D. So the valency can expand. Why the valency can expand in case of phosphorus? Due to the presence of vacant d orbital. Why that valency cannot be expanded in case of nitrogen? Due to the absence of vacant d orbital, because there is no vacant d orbital. So no expansion of the valency. While in phosphorus there is vacant d orbital, so the valency can be expanded. These s electron may be jump further. The same will be the case in other elements, that the group number 16, 17, and the 18. The first element in group number 16 that can form only these two bonds due to the presence of these two unpaired electrons. Similarly, in group number 17, the first element of the fluorine, that can form only one bond due to the presence of that one unpaired electron. One covalent bond can be formed by the fluorine. In group number 18, there is no unpaired electrons, so they cannot form any bond, right? So the next element in all these group number 15, After nitrogen, the next element phosphorus, arsenic, like that. In group number 16, the next element after oxygen is sulfur. Sulfur can expand their valency by jumping this paired electron in the vacant d orbital, which is present in sulfur, not in oxygen. In group number 17 also, these electron can be unpaired due to the presence of vacant d orbital. Like that, in group number 18 also, these can be unpaired according to the Neil Bartlett experiment. In case of the xenon, some bond can be formed. But now the question is, which which type of surrounding element must be present around the central atom? If the phosphorus, sulfur, which have the vacant d orbital, phosphorus, sulfur, chlorine, argon, if these are the central element, then which type of surrounding element must be present? Which have the surrounding element must be of such nature which have the tendency to unpair these paired electrons, जो इन पेड इलेक्ट्रॉन्स को अनपेड कर पाए, जो बाहर की तरफ इनको ले जा पाए, जो न्यूक्लियस से इस अट्रैक्शन को तोड़ पाए. So such type of element if present around these central atom, that is for the around the phosphorus in group 15, around the sulfur in case of group number 16, around the chlorine, bromine or the iodine in case of group number 17, around the xenon in group number 18. If such type of element which have the tendency to unpair these paired electron, then and only then these paired electron can be unpaired. Means the question may be asked in your examination, which type of element must be present around these element like phosphorus, sulfur, chlorine, and xenon, so that these paired electron can be unpaired. These electron must be the electronactive elements, because electronactive elements are those elements we have already discussed during the characteristics of the sp, d and f block elements, which have the tendency to pair these unpaired electrons, which have the tendency to pair the unpaired these paired electrons. Okay, because we all know in the Neil Bartlett experiment, which is done by the Neil Bartlett about the group number 18, when he heated the xenon, when he heated the xenon with oxygen, with fluorine, then and only then the compound can be formed, not in case of the other elements, because the fluorine is the most electronactive element, oxygen is the second most electronactive element. So fluorine has the tendency to unpair these paired electrons in case of the group number 18. So these more electronactive element like fluorine, oxygen have the tendency to unpair these paired electrons, right? Because the size goes on decreasing on moving left right, we will discuss it later on. But these are the basic fact which we must have to kept in mind altogether. Next, we will see the electron configuration for the d block element, that also called as the transition elements. The general electron configuration is n-1d 1 to 10, ns 0 to 2. First of all, we will write the element just before the d block element. The d block element starting from the scandium, atomic number 21. But before writing the electron configuration of the element scandium, whose atomic number is 21, we have just written here the configuration of element, that is atomic number is 20, just before that of the scandium one. So the configuration by using all the rules, that the Aufbau principle, the Pauli exclusion principle, Hund's rule, by using all these things, we just write the configuration for the calcium, that the 1s2, then 2s2, 2p6, 3s2, 3p6, and 4s2, right? After 4s, which have the least energy, in which the electron may be filled, that the 3d, that will be the 3d. After that, the vacant orbitals that is present. Why we have not filled the electron in the 3d and we have just filled the electron in 4s? Because there is the third shell. In third shell there is s, p, and the d. Because according to the Bohrsbury rule, we can explain it, because the energy of 4s is less. Energy of 4s is less than that of the 3d. That's the reason, according to the Bohr principle and the Bohrsbury rule. That's why we have filled the electron in 4s and not in the 3d, because the energy of 4s is less as compared to the 3d. But after filling that electrons in the 4s, now the next one whose energy is lesser is the 3d. Now the electron will enter into the 3d, and the position of that one is just before that of the 4s. After entering the electron into the 3d, that particular d subshell orbital will experience something attraction from the nucleus. So due to that attraction, we will write it here just before the 4s, right? So the valence conjugation for the scandium is 3d1 4s2. That's the diagram here. You can see the 3d, 1 electron, 4s2. Next element scandium, after scandium, that is a titanium, 3d2 4s2. Now the diagram here is, now there are 2 electron in the 3d here, 2 electrons, right? Means number of unpaired electron goes on increasing. Vanadium, atomic number 23, 3d3 4s2, means 3 electron in the 3d. The number of electrons in the valence 4s subshell remains the same. So the attraction between the nucleus and valence shell almost remain the same, right? Number of shell remains the same. That is the four shells here. For the after vanadium, that is the chromium 3d5 4s1. First of all, because we next element 24 conjugation will be must be 3d4 4s1, but you can see here, if we back jump one of that 4s electron into that 3d, the 3d becomes the half-filled stable configuration. Because of that, the configuration, that's the exceptional configuration for the chromium here is 3d5 4s1, not the 3d4 like here, that not the 3d4 4s2, but the configuration becomes 3d5 after jumping that electron into the 3d. 4s electron jump, one of the 4s electron jump into the 3d vacant 3d to acquire the half-filled stable configuration, right? Just we will change here, right? So the configuration for the manganese, next one is 3d5 4s2. You can see here. For iron, 3d6 means the Hund's rule follows. Now the pairing takes place. Initially, first of all, the electrons are filled up singly among these degenerate orbitals of the 3d. All are the degenerate orbitals. All the orbitals of the 3d have the same energy. They are degenerate orbitals. So among the degenerate orbitals, the electrons are first of all filled up singly. Then the pairing will start according to the Hund's rule. That's why we are showing these electrons in such way. Next is the cobalt. The electron configuration is 3d7 4s2. You can see the diagram here. Means we are following the Hund's rule of maximum multiplicity. Nickel 3d8 4s2. But in case of the palladium, which is just present below the nickel in the periodic table, these 2 electron jumps back in these d orbitals, because palladium is present just below the nickel in the periodic table. So the valence configuration of the palladium is 4d8 5s2, 4d8 5s2. But these 5s2, these 2 electron jumps back in the 4d. And the configuration of the exceptional configuration for the palladium is 4d10 5s2 due to their fulfilled stable configuration. In case of copper, the configuration must be 29. There is 9 here. So the 3d9 4s2, but one of the electron jumps back into the D. So the configuration becomes 3d10 4s1. So due to the fulfilled stable configuration. So that's the exceptional cases. There are some exceptional cases in the configuration. One for the chromium, the configuration must be 3d4 4s2, but the real configuration is 3d5 4s1. You have to write it in your examination. What is the configuration, valence configuration for the chromium during the competitive exam also? You will tick on the 3d5 4s1 for the chromium, and for the palladium you will tick on 4d10 5s0, and for the copper you will tick on 3d10 4s1, right? Similarly, you have also read and also learn the elements which are present below chromium in their periodic table will also have that same half-filled stable configuration. The element which are present below copper will also have that fulfilled stable configuration, means copper, silver, lead, copper, silver, gold. So copper, silver, and gold all have that fulfilled stable configuration like that. Means for silver 4d10 5s1, 4d10 5s1. Just increase one number because silver is present just below the copper and gold is present just below the silver. So configuration becomes 3, 4, 5d10 and 6s1, right? So in that way you can learn the electronic configuration and you can write the electronic configuration of the d block elements. Okay, the last one here is the zinc. Group number 12. So the configuration is 3d10 4s2. That's the diagram for that one. Okay. So the one more thing here is that the copper shows the two oxidation state. Means plus one. If it loses one electron, here, loses one electron. So configuration of the Cu plus one ion is 3d10 because the electron lost will be from that 4s. That is very important question. Why the electrons first filled in 4s? You can see in case of calcium here, the electrons are first filled in 4s, not in 3d, not in 3d. Okay, due to the less energy of the 4s, that's the region here. According to the Borsbury or the Above principle, the energy of 4s is less than 3d, so electrons are first filled in 4s, not in 3d. You can explain it by using the Borsbury rule. N plus L rule means lower the N plus L value, lower will be the energy. If the N plus L values are same, then lower the N value, lower will be the energy. These are the two basic things about the explanation of that thing. And after entering, energy of 4s is less than 3d. Okay, but after entering the electron in the 3d electron shows attraction with the nucleus and they come just inner to that of the 4s. Now the energy of the 4s after entering the electron in the 3d, the valence shell is now is 4s. Now if there is any possibility of losing electron, so first of all electrons will be lost from that valence 4s and not from the 3d. Okay, so that's why the electronic configuration of the Cu plus 1 ion will be the 3d10 4s1 because the one electron which will be lost, that will be from the 4s and not from the 3d. The next oxidation state can be shown by the copper, that is the plus 2. You can see here the next electron now can be lost from the d subshell. Now the configuration become 3d9 4s0. Similarly, the zinc can show the oxidation state that is only plus 2, not the plus 1. So these two electrons will be lost from 4s, not from 3d. Because of that, the same region, because the valence shell in the zinc is 4s and not the 3d. Because of that region, because the valence shell is the 4s, because the farthest shell from the nucleus, that is the 4s, so the electron will be lost from that farthest shell, farthest subshell, that is the 4s. So the configuration of the Zn plus 2 will be 3d10 4s0. You have learned these basic fact. Okay. Now we have a simple definition, that is the transition elements. What are the transition elements? The elements which have the partially filled d subshell. The elements which have the partially filled d subshell either in the neutral state or in ionic state, called as the transition element. You can see all these elements from scandium to zinc, scandium to cobalt or the nickel. You can see there is no problem about the partially filled d subshell. The d subshell are partially filled in the neutral state, right? But in case of copper and zinc in the neutral state, you can see in case of copper the d subshell is fully filled due to their exceptional configuration, that is the 3d10. And in zinc the 3d10, that is the full filled in neutral state. But in ionic state, in copper plus 1, that is D is fulfilled, but in copper plus 2, the D subshell is not fully filled, that is partially filled here. So in the ionic state, in one of the ionic state, if the D subshell is partially filled, then it come in the category of transition element. But zinc is such type of element in which you can see that D subshell is always fulfilled, whether it is present in neutral state or in ionic state. Ionic means in plus 2 oxidation state, which is the oxidation state of the zinc, which can be shown by the zinc. So the zinc is not the transition element. So the statement generally been asked in your examination, all the D block elements are not the transition element, but all transition elements are D block elements, because transition element तो D block element हैं, लेकिन सारे के सारे D block element transition element नहीं है. For that you must have to give these examples, that is of copper and the zinc, in the example form to explain that particular statement. You don't just write the answer in wording, but write these configuration also. Okay. So that is about the general electron configuration or electron configuration of all these elements of the D block, right? Next, as I have already told you, the zinc, cadmium, mercury, they have, because below zinc in the D block, cadmium is present, and below cadmium, mercury is present. In all these elements, whether zinc, cadmium, or mercury, there is no partially filled d subshell, no partially filled d orbitals, so they are not considered as transition series elements. The metal liquid in these d block element is the mercury. That is a metal liquid. Next, we will see here some basic thing again. The general electronic configuration for the d block element is n-1 d1 to 10 ns0 to 2. So you can see here the ns0 to 2, 0 to 2, ranging from 0 to 2 means 0, 1 and 2, right? So that 0 for what 0, for what 1, for what 2. The 0 is for palladium. In case of the palladium, the configuration is 4d10 5s0. So that's why we have written here 0. Okay. And in case of chromium, in case of copper, you can see here there is one electron in the valence, आपकी 4s subshell here, that 1. Similarly, for the other element present below it. So that's why we have the ns0, 1, 2. Okay, and 2 for all other elements. You can see in all other element here in the diagram also, there is 4s2, 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 1 for chromium, 4s2, 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 then 1 for copper, then 4s2 for the zinc also. Okay, so these are some basic fact we have written here separately because they are very important for the examination point of view also. You must have to learn all these facts. Okay. Next are the 4f block elements, the elements in which the last electron enters into the anti-penultimate F subshell called as the F block elements. If that there is a proper name of that anti-penultimate F subshell, if that F subshell is 4F, then they called as the 4F block element, and they are also called as the first transition series element because they form the transition series within the transition series of the D block element. D block element की जो transition series है वहीं से ये निकाले हैं हमने, और they are placed at the bottom of the periodic table. That why they called as the inner transition series element, and that is the first inner transition series. Originally, these lanthanide are called as a rare earth because they are present in very minute amount, very less amount in the earth crust originally. Now, due to the researches, we have extracted some of the element, but it is very difficult to extract, also extremely difficult to obtain it in the pure state. They are present in very, very less amount. That's why originally they are called as the rare earths. So here is the electronic configuration of all the elements of the 4f block element. Because that 4f block element that started from the cerium, whose atomic number is 58, ranging up to the lutetium, that is atomic number 71, because they follow the lanthanum, whose atomic number is 57. That's why all these 4f elements called as the lanthanides. That question may be asked in your examination also. So the configuration for the cerium is 4f1. You can see here 4f1 means that electron, that is the last entered electron in the configuration. That's why they called as the F block element, 4f block element, because the last electron enters into that's the valence one. Valence here is 6s. Just inner to it, that is the penultimate position, that called the 5d, and just inner to it, that is the anti-penultimate position, that is the 4f. That's why we are saying in the definition that the last electron enters into the anti-penultimate 4f subshell here, right? So that's the last entered electron. So the configuration for the cerium is 4f1, 5d1, and 6s2. Okay. In case of the praseodymium, the configuration should be 4f2, 5d1, 6s2, but there are some exceptional cases here. So there are some elements in which the electron is present in 5d, that is the cerium, that the gadolinium, and the lutetium. These are the elements in which the electron is present in 5d. That's why in the general configuration we have written the one electron in the d5, आपकी 5d, that is 0 to 1. In some cases the electrons are 0, in some other cases there is no electron in 5d. But there can be some exceptional cases also. You can see here there are many exceptions in the electronic configuration of the 4f element. Similarly, also for the 5f element, we will just see later on after the 4f block elements. So the configuration for the neodymium is 4f 4f4, you can see here 4f4, 4f4. Here are some basic facts. Means, for example, you can see here in case of the gadolinium. Why gadolinium shows +3 oxidation state? The common oxidation state of these all F block element is +3, right? But the why it shows the +3 oxidation state? Because after losing these 3 electrons, it acquires the half-filled stable configuration. Similarly, why lutetium shows +3 oxidation state? Because after losing these 3 electrons, it acquires the fulfilled stable configuration. Why ytterbium shows the +1 oxidation state? Because after losing that one electron, it acquires the fulfilled stable configuration. Like that. Means such type of question where the answer just be given on the base of half-filled stable configuration or the fulfilled stable configuration. You have to learn these basic fact. Okay. Now the next one for the 5f block elements. So the 5f block elements are those elements in which the last electron enters into the anti-penultimate F subshell, called as the F block elements. Called as the F block elements. So these are the F block elements. The from ranging from thorium atomic number 92 to lawrencium atomic number 103. Similarly, you can write the electron configuration for these 5f elements. So we have just drawn here. Or same type of question may be asked from these 5f block elements. Okay. So just write down in your copy and draw these electron configuration, and same type of question must be learned. Next, the main topic that will be the screening effect or the shielding effect. Or next one is the penetration power. These are very important topics that we will discuss in our next lecture. That is very important lecture because on the basis of that we can explain the different properties. So keep on watching. For the next lecture, we will discuss about the screening effect and the penetration power. Thank you.